So let's start off by taking a look at a relatively simple example problem for Module 9 for ME 270 Structural Dynamics. So in this problem here, all they want us to do is use Lagrange's equations to find the equation of motion for the system shown here. And in the system, we can see, okay, we have a mass, we have a spring, we have a damper over here, we have this distance q here, and this external load p times the sine of omega t. So we just need to get this in the right form, put it into Lagrange's equations, rearrange and solve for our equations of motion. So within this, it's a 1 degree of freedom system here. So we're going to let our u equal to q. And we can see here, for this equation here, we now have our kinetic energy equation. T is equal to 1/2 mq dot squared. And we have our potential energy here, V, is equal to 1/2 kq squared. And then we have our P is equal to negative CQ plus P times the sine of omega t. So for our setup problem here, I redraw out my given diagram. Again, here I have my spring constant K. I have my damper with our value C. We have our Q value here, our mass M, and our external load P times the sine of T. We have our relationships over here for U, kinetic energy and potential energy, and our P. Again, we want to use Lagrange's equation for this 1 degree of freedom system. So now we can begin our solution. And as we start our solution, we can reference back to our problem statement and our setup page for information that we may need and what we're looking to solve for. The next thing we want to do within the solution, though, is come up with our key equations and our governing equations. So we've already determined that we have our relationships here for potential and kinetic energy and our P equation here. So our next key equation is going to be Lagrange's equation. Now this comes from page 223 of our textbook, equation number 8.9. So I've written it out here by hand, and I've also typed it out here as well at the bottom, a little bit neater and easier to follow through. So for Lagrange's equation, what we have is our derivative d over dt of the partial of t with respect to our q dot sub I minus the partial of t with respect to q dot sub I, with q sub I, plus the partial of v with respect to q sub I is equal to p sub I, where I is equal to 1. And again, this is from equation 8.9 on page 223. So now what we need to do is now we can see why we have these relationships up here for our t and our v, is because these are going to need to be plugged in down here to these partials within Lagrange's equation. So we could have started off with Lagrange's equations and then realized we needed to have these relationships as well to plug in. So as we begin our solution, I write out our T, V, and P, plugging in for our specific Q's for our problem here based off of our given initial diagram. So we can plug those all in there. So now we have expressions for T, V, and P here. So now we can start with our general form for Lagrange's equation that we just took a look at here, equation 8.9 from our text. And we can start plugging in for our T's and our V's. And our P as well. So I've color coordinated all of these just to make it a little bit easier to see where we're plugging in. So if I have the partial of T with respect to Q dot sub 1 here, I can take my T equation from up here, plug that in right there, and that's where this comes in here. Same thing for this T here. I plug it with my expression for T from up above, and my V, I plug in here from this expression here, 1/2 kq squared. And then for my P here, I'll wait and plug that in the next step, and that comes from this guy here, so I can plug in right there for my P. So I have d over dt of my partial of now this expression for T here, 1/2 mq dot squared, minus the partial with respect to q sub I of my T of 1/2 mq dot squared there, plus the partial with respect to q1 here of my V term, which is 1/2 kq squared is equal to P. So then I go through and I can do out my partial derivatives and then do out my full d of dt here. And when I do out that math, the left-hand side of my equation now becomes mq double dot, when I do out my derivatives here, plus this becomes 0 for the middle term, plus my kq from my derivatives over on this term here is equal to the right-hand side of the equation, which was from up here from P, which is a negative cq dot plus P times the sine of omega t. So that right there we can simplify, get rid of our 0 there. So we have now our m, rearrange a little bit, q dot double dot plus our cq dot plus kq is equal to P times the sine of omega t. So there's our Q double dot, Q dot, Q form here is equal to our P times the sine of omega t on the right-hand side of our equation.